and during his thesis, he was part of the early and groundbreaking and laying investigations on spin qubits in quantum dots. And after a postdoctoral stay at IBM in York Heights, he became professor first in Basel and then in Aachen. And since 2008, he's a full professor at the University of Constance. He's an expert in solid-state quantum information processing and generally in the study of spins and their dynamics and decoherence and interactions in solid-state systems, and of many different types. And he will today present kind of an overview talk on quantum computing with spins in semiconductors. And so great that you're here, and we're looking forward to your talk, Guido. Please go ahead.
Thank you, Geza. Thanks very much for the kind introduction, and also thanks for the invitation to come here. I'm actually here at the IPC, so if anyone is interested in discussing with me, I'd be more than happy to join in discussions. So I'll talk today, as Geza said, I'll try to give you an overview over what's going on with quantum computing with spins in semiconductors. And this is supposed to be an overview, and maybe I won't cover all the things that I wanted to, but I also welcome, of course, discussion if you have questions. I don't know how it works during the talk or at the end. That would be great. So, so what is the maybe here's something that you may know, and it's actually not that new anymore. So one of the most advanced systems for quantum computing nowadays is actually a solid-state system, but it's not a semiconductor system or not a spin system, but a superconducting processor. And then this is this quantum supremacy work by Google, and you see it's a fairly big team. So this is the chip. It's about 1 centimeter across, and if you know this team here, this list of authors is very impressive if you're at the university or maybe public research institution. But if you ask, the CEO of Google, what he said actually is it's a relatively small team. So that maybe makes us hopeful that they could go on and scale up further from this milestone in the future. And so because this is a kind of a colloquium talk, I guess everybody knows what quantum computing is, but just in case to sort of be on the same page, I have a very small introduction into what is it actually that we are trying to achieve. And one example is this factoring by Peter Shor. This is one of the most famous quantum algorithms where you have a big number as shown here. And what you're trying to do is to split it up into prime factors. And if these numbers are large and the prime factors are large, this is actually a difficult problem, which is important for cryptography. And what we're trying to achieve is to somehow store this input. And in general, this is true for all quantum or for most quantum computations, that one stores some input into a quantum state and then runs this quantum state through some quantum system that does a computation, some kind of time evolution. And then there's a state coming out that you can then measure and then get the result out. And the physics is, of course, contained in this big box, the quantum time evolution, which is actually, it's a complicated control problem. There's a Hamiltonian here. If you have a very complicated computation, it's not an easy task to find this time-dependent Hamiltonian that does the job for you. So that's in some sense the problem. And actually, what makes the problem a bit easier is to divide the problem into smaller pieces. And this is the same actually one does in classical computation, to divide up this big quantum evolution into smaller elementary pieces of quantum evolution, so-called quantum gates, that act only on, let's say, a single qubit here, like in this blue box, or on 2 qubits with these symbols here. And it's actually possible to show that this is sufficient to assemble any possible quantum computation. And so what actually these diagrams mean is that this is kind of describing the time evolution of a discrete set of quantum bits. So basically it's a space-time diagram, if you wish. The space is discretized. It's just a discrete number of bits in your quantum register, or qubits, quantum bits. And then these are the gates that act at a certain point in time. There are 1 qubit gates, 2 qubit gates, and then, as I said, this is all you need. All right. So what else can you do? I mean, the example I showed is factoring. This may be a bit of a destructive example because it breaks codes, but one can also do other things. And the one thing that I find particularly interesting is that quantum computers could potentially simulate other quantum systems. And because this is interesting because it's known, of course, that the simulations of quantum systems with regular computers are extremely hard. And so this was in some sense one of the initial ideas that led into the development of quantum computers. And so recently, just a few years ago, there have been a number of advances where this has actually been realized for small systems, in this case, molecules with 2 or 3 atoms on a small quantum computing systems. This is already in some sense outdated by now. People can treat bigger systems. So this was just supposed to be an example. And one thing I wanted to briefly explain, just because I'm going to need it later in my talk, is the controlled NOT gate. So this is this one gate that acts on 2 qubits, and this is the only gate you need that acts on more than 1 qubits in order to do any quantum computation. And so basically it involves 2 qubits. One is called control, the other one is called target. And basically what it does is flips the target qubit if the control is in the 1 state. So that's what it does, but that's in some sense a classical description of the gate. It can also act on superposition. So if the control, for instance, is in a superposition of 0 and 1, it would create the superposition of the corresponding outputs. And what you see here is already something that is typically quantum, namely that you cannot write the state as, what is the state of the control after the gate and what is the state of the target after the gate. These cannot be separated anymore. And such a state is called entangled. And of course, nowadays, everybody knows what entanglement means. It's one of the substantial ingredients of quantum computation. Everybody learns this. Even babies learn it nowadays. That's why everybody knows it. So I want to summarize, and then I'll actually I will become more specific on my topic. But just to summarize, I wanted to tell you my take on what Google achieved. I think this was this 2019 quantum supremacy demonstration was really a landmark demonstration. It involved more than 50 functioning superconducting qubits arranged in such a 2-dimensional grid. It was important because and it also sets it apart from earlier demonstrations. This is a fully programmable quantum computer, so you can run any sequence of quantum gates on it as you please. And the fidelities of these gates are fairly high, so greater than 99%, so that the probability that an error occurs if you do a single quantum gate is less than 1%. This is much better than anything that had been done before on such a big machine. But of course, compared to what we have on our classical machines, this is still fairly poor. I mean, you would expect much higher fidelity, and that's also what we're aiming for in the future. What they did in practice is actually a computation that is not very useful. It's just something that is impossible with the best classical computers, and that's what they call quantum supremacy. They claimed that in order to do what they did in a few minutes on this quantum machine, it would take a classical supercomputer about 10,000 years. The supercomputer they compared to was actually installed by IBM, and IBM, because they're competing with Google, later corrected this and said, well, if you use your hard disk space cleverly, you could also do it in 2.5 years. But still, even considering that, I think it's an amazing achievement. So it's a proof of principle, not a useful computation. What they actually did is they ran some random circuits. But what I find also important looking at the hardware is that these qubits are really, really big. So every qubit is about 0.5 millimeter large. And that's actually why for these 50 qubits, you need a chip which is 1 centimeter across. So these are really big systems, and that actually makes it a bit questionable how you would scale it. And so what I'm going to talk about is another working universal quantum computer, which is based on electron spins in silicon quantum dots. And my argument here is that these are really truly nanoscale objects, and therefore they are in principle scalable to large numbers of qubits. And then what I'm really showing you here is something that was experimentally demonstrated 3 years ago. So even before the Google experiments. Now, what's the catch? The catch is that it only has 2 qubits. So we're not at the point, one has to say, as the superconducting qubits in this respect, but work is ongoing, and by now people have 4 coupled qubits, and they're working on bigger systems. Another thing that one has to say is that the gate fidelity in this first demonstration that I'm going to show you has been only 80%. That's very poor, but this was very soon improved, and we have recently seen new experiments that have also went beyond the 99% fidelity threshold. And then maybe another anecdote that I'm going to tell, and then I'll become a bit more serious. So actually, what's interesting is that John Martin is the lead researcher in this Google team. Is now not with Google anymore, and he actually joined a silicon quantum computing team some time ago last year, and so this is spin qubits. It's kind of interesting. All right, so here's what I would like to talk about. I'll give you a quick intro into spin qubits. I'm a theorist, so it's going to be mostly theory, but I'm going to report a lot on experimental results. And then I'll walk you through a few issues that one has to think about that also, I think, incorporate interesting physics. And I'll get to this universal 2-qubit processor that I was telling you about. I'm not sure I will get to the last part, which is interesting, but I can just give you a brief outlook here. So maybe also, again, to embed it a bit into what other systems there are, you could divide up quantum computing hardware into atoms, and this is basically atoms in ion traps. Mostly this is also using the spin degree of freedom. And then there are solid state systems, either spins in semiconductor systems, in quantum dots, or as defects, or superconducting circuits, which I've just briefly mentioned. And so there are various players in these different areas, different university groups, but also companies. For instance, Intel is interested in semiconductor realizations, which makes sense for them because they're a semiconductor company, and Google and IBM are building these superconducting processors. Microsoft is doing something combined, super and semi. So let's get to spin. So spin is actually not, spin is the first qubit, if you wish, that people have thought about. Just when spin was predicted by Pauli, he had this very convoluted language. He talked about the peculiar and non-classical two-valuedness of the quantum theoretical properties of the outer electron of some alkali elements, and of course, nowadays we are much more efficient with language, right? We just call this spin. And actually, more recently, whenever we have a non-classical two-valued system, we call it a qubit, right? So that's how we would call it nowadays. And it's actually interesting, just a little bit of history, that Sam Houtsmith, who was one of the experimenters who discovered spin and later became the editor of PRL, one of the founding editor, he once wrote that the quantum. So when he was telling about their old paper from 1925, he said, well, the quantum numbers they used for the spin was ms, and ms is plus minus 1/2, but in those days they called it 0 and 1. So that I found actually quite interesting, because nowadays we're going back to 0 and 1. We want to use this, of course, as a bit. And so in principle, you could use any kind of spin system as a spin qubit. Typically, spin 1/2 is good because it has 2 values. It could be an electron spin. That's what we're usually thinking about. Could also be an atomic nucleus. And you just identify the spin up state with the 0 and the spin down state with the 1. And you can then describe any state of this qubit, which can be any quantum superposition of these two states as a point on the surface of this Bloch sphere, of this unit sphere. And this just tells you that you have, in some sense, more bigger state space than for the classical bit, which only has the north and the south pole of this sphere. Okay, and the reason why we're using spin is that it's a magnetic moment, and it's not directly coupled to electric fields, which are often very noisy in semiconductor or in general solid-state systems. I'll say a few more words about that. That also makes it a bit harder to control them, and that's the usual trade-off you have with quantum information processing. So there are a number of different systems that you can think about. The sort of most common one, and the one that I'm going to be talking about mostly here, is electron spins in three-dimensional semiconductors these electrons are then confined in a quantum dot to kind of store them in a specific place. So their motion is confined into a zero-dimensional location, in just a position, so we can address them at one location. Another possibility that's been proposed around the same time and has been explored also very actively is nuclear spins. And these nuclear spins have very long also coherence times. Another recent development is the use of hole spins in semiconductor rather than electron spins. And this has a number of advantages. And this is actually a very fast growing field recently. And I'm not going to go into this topic for time reasons, but it's actually very interesting. There are other systems like defect spins in diamond or spins in 2D materials that may be interesting for some of you here. And I'm not going to talk about all this. It would just take too long, but if you want, we could talk about this privately if you like. So I'll basically stick to this regular semiconductor spin qubits, and you can envision a typical setup like this. This is a theorist's drawing, of course. You have a series of quantum dots that are defined by these electrodes, metal electrodes in dark blue, and they control, basically, they define the confinement potential, and they also control the coupling between these dots that each contain one electron that represents then the qubit. And a simple Hamiltonian that would describe such a system would be that of an exchange coupling between neighboring spins. With this exchange coupling could then be controlled as a function of time by applying time-dependent gate voltages to these electrodes. And then a means of addressing single qubits for the single qubit gates would then be some sort of local Zeeman effect that you would have to control locally. I'll get back to that later. And so if you really have both of these control mechanisms, then you can use the exchange to perform 2-qubit gates. And that has been shown initially about 15 years ago. And the state of the art, as I already mentioned, is that these 2-qubit gates can now be performed. This is very new from this year with fidelities greater than 99.5%. The local Zeeman effect can be used using electron spin resonance to perform single qubit gates, basically rotating single spins. And by now, this can also be done with actually quite impressive accuracy. And I will show you a bit more about how this is usually being done. If you have both together in the same system, which is not always the case in these demonstration experiments, then in principle, you can do universal quantum computation. Right? So you have these two ingredients that you need to assemble any type of gate sequence, any type of algorithm. So the workhorse early on in the field was gallium arsenide or other 3-5 semiconductors, because this just is available with very, very high purity, and the technology of making quantum dots was most advanced in these systems. But people have done first this single speed readout, and then they were able to measure the spin lifetime, how long the spin state survives. For instance, here as a function of magnetic field. Single spin rotations were achieved, as I mentioned before. These elementary 2-qubit operations were shown, and relatively long coherence times, but you see already these coherence times are fairly limited in the nanosecond range. And so this is actually one of the problems. And so here comes the first challenge. What could go wrong is that in addition to your electron spins, even if you manage to fill all the quantum dots with a single electron, your material consists of atoms, and these atoms also have spins. They're nuclear spins, and the hyperfine coupling typically couples you to these large number of nuclear spins. If the dots are large, then the electron wave function will overlap with many nuclear spins, and this leads to a electron spin dephasing. And the typical time here is called T2 star. This is the basically the Ramsey fringe decay time, or the free induction decay, due to these randomly oriented nuclear spins. And so this is a problem, and one of the solutions to solve that problem is to look for materials where you don't have that many nuclear spins, and that's actually what's happened in recent years. So here's a summary that I took from a slide from Lieven van der Sijpen. So here's your gallium arsenide from the early experiments with a T2 star time of typically about 10 nanoseconds. So that's how long you can use your qubit. You can echo out some of that dephasing and improve on that. But that still limits you to a certain like 200 microseconds, and actually it's something that doesn't always go well with qubit operation. And so what this led basically to the development that most experiments are nowadays done with silicon, which has an isotope mixture which is much more favorable, because it only consists of about 95% of silicon-28 if you take natural silicon that is nuclear spin free, and then you have this remaining silicon-29 nuclear spins that do cause some dephasing, but that's much weaker. And then of course people go even further and nowadays purify silicon isotopically to fairly high amounts, and then increase the coherence time again substantially. Another thing that you can do once you are there, you can also put back some nuclear spins in a controlled way. So the phosphorus nuclear spin, for instance, is a nuclear spin 1/2 that you could then use as a qubit itself if you can control it individually. And these nuclear spins have extremely long coherence times. And so you can ask, what does it have to be silicon? What kind of materials could you take? So gallium and arsenic are not good candidates. So this red number here in this periodic table shows the fraction of naturally occurring nuclear spin-free isotopes. And for the group 3 and 5 elements, because of an odd number of nucleons, you typically only have nuclei with a finite nuclear spin. The group 4 elements are much more promising, because they usually have a very abundant nuclear spin-free isotope. So carbon, for instance, has 99% C12, and that makes it interesting for qubits. Silicon, as I mentioned, or combinations of both, and also other materials that are very typical for 2D semiconductors, such as the transition metal dichalcogenides. They could be very promising in terms of nuclear spins. One problem that you sort of acquire when you move from gallium arsenide as a simple direct bandgap semiconductor, basically here the first Briand zone in K-space shown here with the Fermi surface, very simple. Makes it easy to confine a particle in space and then only be left with the spin degree of freedom, and then you have exchange coupling in this simple Heisenberg form. This becomes more complicated if you have, for instance, silicon. It has a multi-valley structure in the conduction band, and that can be, it can be somewhat simplified in heterostructures, but still has a multi-valley structure. And then this valley degree of freedom will still be present if you confine your electrons, and this valley degree of freedom can then interact with your spin, for instance, in the exchange interaction as shown here. And so that can be, you can view it as a feature, but to first approximation, this is a bug. This is something that will disturb your spin dynamics. All right, so that's the material. Let's say we are in good shape in terms of our material. We have gotten rid of the nuclear spins in some way. And then what is another problem? Another problem is that I simply said, in order to do single qubit gates, you have to apply a magnetic field to a certain qubit spin, and that's actually not so easy if you really have to do it with a magnetic field. And so that's why we like to operate with systems that control the spins with electric fields, but that's actually exactly what the spins are designed not to do, to react to electric fields. And so that's something you have to engineer. And so maybe that's the next topic, the electric control of spin. How do you use electric fields to do single spin rotations? So the standard way to rotate spins is electron spin resonance, which means you apply a static field Bz, and then you apply a perpendicular oscillating field Bx with a frequency omega, and the frequency matches the Zeeman splitting. And so if you do that, you will get magnetic resonance, and you can basically rotate the spin. But the problem is, I mean, this was achieved, but it was really a tour de force, and it's probably not very scalable. These local oscillating fields are very hard to achieve. You need some, you can't just use an external microwave source, for instance, because it will just irradiate all the qubits. You would have to build some nanostructures that carry large currents, and so on. It's not easy. Much easier would be to just apply oscillating electric fields or oscillating voltages, because you have these electrodes very close to the confined spins. But the problem is that the electron spin, of course, has a magnetic dipole rather than an electric dipole, so it doesn't directly react to your oscillating electric field. So the way around that is that the electron motion has an electric dipole, and then somehow, if you can somehow couple the electron motion to the spin, you can actually endow the spin with an effective electric dipole. And so one mechanism that does that is spin-orbit coupling, and that has indeed been used, in particular in gallium arsenide, where it's been first demonstrated by the Delft group here, Katja Novak. And this is what's been used in gallium arsenide. There's sizable spin-orbit coupling. It can be done with silicon. So this is the second paper, but actually the problem is that in silicon, spin-orbit is rather weak because it's a lighter element. The same holds true for carbon. There's some trick here that uses the Valley degree of freedom, which is kind of clever, but it's probably not it's not the easiest way to do single spin rotations with electric fields. Another possibility that I'd like to show you is that you use some form of synthetic spin-orbit coupling together with this electric dipole spin resonance. And synthetic spin-orbit coupling means that you use a magnetic field gradient. So you use a magnetic field which depends on space. So this is usually done with a nearby ferromagnet, a micromagnet that's put on the chip. And a position-dependent field can be basically understood in this way. So you can Taylor expand this position dependence. And what you see here is that there will be a term that couples the position of the electron to the spin. And that's like a spin-orbit coupling. And one can use that then, if you use an electric field, to rattle around the electron in its confinement potential. It will effectively see a time-dependent magnetic field, and that's you can use for magnetic resonance. And this is really the method that has been used here, mostly by the Tokyo group of Seigo Tarucha, and also by the Delft group, to make these very high fidelity single qubit gates. All right, there's another extension of that, which we've been studying, in recent years, which is the flopping mode spin qubit. So what we mean by that is simply a single electron in a double quantum dot, that's shown here. So it's a double well potential. There's a single electron in there, and because it's just one electron, it has the freedom to move from the left to the right. So that is its degree of freedom connected with motion. And then the entire system is put into a magnetic field gradient. And so this means that, so first of all, the fact that it's two dots and the electron can move between these two dots means that there's a larger electric dipole. And it's also switchable, because if you can then control this double quantum dot, as shown here, you can basically decide if the electron is allowed to move or not. So you can switch this electric dipole on or off. And you remember one of the advantages of spin qubits is that they don't talk to electric fields. And so if you want to just store the qubit, you'd rather not have the electron the electron spin talk to electric fields. And so then you just park it by biasing the double dot very strongly, and it just sits there and cannot move. And if you want to couple it to your electric field to do a spin rotation, you would move it to this symmetric position where it's in the flopping mode, it can go back and forth, it couples to the electric field while you're making your single qubit gate. And there are other advantages like charge noise sweet spots, so certain operating points where this qubit is actually insensitive to charge noise, which I'm not going to go into in detail here. So this was work done on the theory side by my former postdoc, Monica Benito, who is now at Augsburg University. Let me just give you a few more details on this flopping mode spin qubit. It's a nice and simple system that I think one can understand fairly quickly. So it's a spin qubit, so it has a spin denoted by this degree of freedom sigma that is either up and down. That's our qubit. In some sense, it's connected to another qubit, which is a charge qubit, namely the information whether the electron is on the left or on the right. This is what I denote with this letter tau. And then the Hamiltonian of the system can be written in this form. It's basically this has this part of the charge, which is given by the energy detuning between the two dots. So this is just epsilon is just the energy difference between the electron being on the left or on the right. And then there's tunneling, which connects the two, which makes transitions between left and right. And that depends then on the height of the barrier. And you can diagonalize this and get an orbital eigenenergies plus and minus omega over 2s. And this is the orbital energy splitting here. And then there's a Zeeman energy that's coupled to the spin. And then there's the magnetic field gradient that couples spin and position, because the magnetic field in x direction in this case is different on the left and on the right. It will couple the position. So this is the synthetic spin orbit coupling. You can then also drive this system. Again, with driving is with an electric field, you will couple to the position, to the charge degree of freedom, tau z, so left or right. Then you can diagonalize this orbital part, and what you will find is that this driving then basically also connects to the spin. If you go to this new basis, and now what you find is that you have two terms that couple to the charge. So you have this. Maybe I should show this first. So these are the orbital eigenstates, the energy levels as a function of epsilon. This is cut away here for some reason. So these dashed lines are just the orbital eigenstates, minus and plus, the bonding and anti-bonding states split by tunneling, and then there's the Zeeman energy that splits spin up and spin down. And then this synthetic spin orbit coupling actually couples the two levels here when they approach each other, the two levels with opposite spins. And if you now drive, so you have now, when you're driving, you have now another term that can make transitions between orbitals. And so you can have these second order transitions. Let's say if you're in spin down here, this is our qubit, the purple and the green line are the qubit levels. You are in the spin down state. The driving will take you, this synthetic spin orbit coupling will flip the spin and take you to the excited orbital state, and the driving will take you back down. And this is effectively how you can make a spin rotation. And you can then calculate the Rabi frequency. For spin rotations, it's proportional to the Rabi frequency for charge rotations times tunneling times the magnetic field gradient here. So this is how one can do EDSR with this flopping mode qubit. And another interesting thing that we discovered, and maybe I'll go through this a bit more quickly. If you put this into a microwave cavity, you can look at the transmission, and this signal here, this is now as a function of the interdot bias and the magnetic field. This tells you about basically this single, qubit energy splitting F01. This is just when the probe or cavity frequency matches this frequency, you get a signal, an absorption in the cavity. And so this is when this phase jump here happens, this feature here. And actually, if you had only an external field, only a Zeeman energy, so this is sort of the formula for our qubit splitting. It's the Zeeman energy far out here, and this is what you see here in the outer parts. If that was if there was no synthetic spin-orbit coupling, this would just be a straight line. And due to this synthetic spin-orbit coupling, you get this this nose here, which is given by this term. This is given by the magnetic field gradient. And then there's another effect, which is that if the electron is on the left compared to the right, it will have a slightly different Zeeman splitting, and that's why these two energies here, these two levels, are at a different you see the phase jump and a different magnetic field. And this is due to this term, which is new, which is actually a longitudinal field gradient. So there's another component of the field gradient which basically changes the Zeeman energy on the two dots. And this can be detected with this. This is connected with these charge noise sweet spots. And so that's just an interesting story that in some sense this cavity QED readout, so this microwave transmission readout of the double dot, is sensitive to these longitudinal field gradients. And that is quite sensitive, made us think about other possibilities that one could use it for. And another one would be to somehow sense a small magnetic field. And for instance, the magnetic field could come from a single nuclear spin. So imagine a situation where you have your microwave cavity, you have your, instead of a double dot, you have a dot and a donor, let's say a phosphorus atom, that is coupled to the electron with a hyperfine coupling, by A here. And so it's actually, it's a bit like such a double quantum dot, but one of the dots is now a very steep, very strong confinement, has a very strong confinement due to this donor potential. And we could then analyze this system, and just to give you a quick summary, what we found is indeed that with current technology, we think that microwave transmission through typical superconducting resonators with such a system built in could detect the state of the nuclear spin by looking at where the cavity transmission or cavity absorption is peaked. In this case, you see here these different cases for nuclear spin up and down that are clearly distinguishable within the typical resolution of such cavity transmission experiments. So that's another sort of direction that you can go into to do hybrid electron spin nuclear spin systems. All right, so this finally brings me to my 2-qubit processor. I have told you about electric control of spins. So these are the single qubit gates. And now I'm going to tell you a bit about how to do 2-qubit gates, how to couple electron spins to make then sort of complete the set of operations that would then be used to perform a quantum computation. And the basis of all this is the exchange coupling between spins, and this is driven by the exclusion principle, the fact that electrons obey Fermi statistics. So it means that you cannot put two electrons in exactly the same quantum state. And what it means for quantum dots, let's say if you put two quantum dots next to each other, and I just denote here the levels of these quantum dots, let's say every quantum dot just has one available level at just the ground state orbital. And you can put an electron in this orbital with either spin up or spin down. And let's say if you have both electrons in, if you have two quantum dots, and in each quantum dot you put one electron with spin up, like shown here in the upper part of this little sketch, then it means you are, well, in the spin triplet state. And what it means is that if now one electron wants to hop to the other dot, it will not work because there's already an electron with spin up there. So this is Pauli blocked. Whereas if the two electrons have opposite spins, or more precisely speaking, they're in a spin singlet, then electron tunneling can actually take you from a situation with one electron per dot to a situation where one dot is empty and the other one contains two electrons, one with spin up and one with spin down. And it turns out that this hopping is, even if it only happens virtually, because of course the two electrons are also charged and repel each other, this can still happen virtually. And this actually leads to a reduction of the energy, basically because the wave function can spread out a bit more. The kinetic energy is reduced, and the amount by which it's reduced can be approximated by this tunneling matrix element squared divided by the Coulomb repulsion. And so the energy difference between these two states is exactly the exchange energy. This is this T squared over U. And this really only depends on the spin state, not on the charge state of the two electrons. The charge is in some sense always one electron per dot, but depending on the spin state, the energy will be different. And so this means I can describe this by a spin Hamiltonian, and I could just write it as basically if the system is in a triplet, the energy is 0 or E naught. And if it's in a singlet, this is what I described by this projection operator on the singlet state, then it's just lower by an amount minus J. And so then we can rewrite this projection operator using spin operators, and what one finds is just the good old Heisenberg spin exchange coupling. And that's of course our workhorse. This is what leads then to the operation of 2-qubit gates. And how this works, I can briefly summarize here. So basically, if you operate this, if you have the means of switching on and off this tunnel coupling here in between the two dots, it effectively means you can switch on and off the exchange coupling. If you do this, let's say switch on the exchange coupling for a certain time, what you find is this unitary operation. It's actually easy to calculate this because P is a projection operator. So this is, now you can choose for how long you want to switch on the exchange. If you do it such that the integral under this pulse is pi, what you will find is that you exactly interchange the state of the two spins. So this is a swap gate. That's interesting, but not sufficient for quantum computation because it's not one of those entangling gates. What you can do is you can switch on the exchange coupling for half the time that it takes to do a swap. So then you get a pi over 2 pulse, or so-called square root of swap, which basically produces a quantum superposition of the original state and the swapped state. And so that's actually an entangling gate. And you can also show that it leads to the formation of C0. So this is what you can do if there's no, what I've assumed here is, by the way, that there's no magnetic field, or what it would still work if there's a homogeneous field. And this can be used to actually produce fairly fast 2-qubit gates. Another way would be to use a gradient field. And we've seen before that it's sometimes useful to have these gradient fields present. You can also do, as we noticed early on, you can do a universal 2-qubit gates using these gradient fields. That's another way. So that's
sorry, I had a bit more than 40 minutes now.
Okay, thank you. So both of these can be used to make 2-qubit gates that then ultimately lead to universal control. So you can build up any algorithm, and both of these are in some sense DC controlled. So you switch on the exchange slowly and switch it off slowly, and much slower than any kind of resonance frequency in the system. Here's another idea that was actually this is actually the basis of these recent 2-qubit gates, and this is an AC control. So basically you have exchange coupling present, and you have a magnetic field gradient, and the field gradient has the following functions. First of all, one component of the gradient distinguishes the resonance frequency of left and right spin. So this then allows you to rotate them with spin resonance individually at different frequencies. Another component of the gradient of the magnetic field gradient creates this artificial spin or synthetic spin orbit coupling that you need then to drive with electric fields, and the middle gate here will control the exchange coupling. And so what you'll find if you look at the spin levels of the system is that you have 4 spin states: up, up, down, and down, down. In a magnetic field, the parallel spin states are energetically split off from the anti-parallel states. And if you then also add the magnetic field gradient, you can split off these anti-parallel spin states. And so this allows you then to rotate the left spin or the right spin selectively using different frequencies as shown here. If you then also switch on the exchange coupling, this will actually effectively lower the anti-parallel spin states. And this will create a transition which, for instance, rotates the left spin only if the right spin is up. And so if you do that, that exactly creates a C0 gate. So if you get such a conditional conditional gate, this is actually the C0 gate. That's exactly what we need. So this is nice. This was then implemented in this system here. This is a silicon germanium system that was built by our colleagues at Princeton in the group of Jason Peda. And just very briefly, so you can then model the evolution of these spins. This is the target spin in red as a so it's basically the probability that the target spin is up. It oscillates. You can then and depending on the control spin, of course, and then you can from comparing here theory and experiment, you can, for instance, read off the C0 gate time, the readout visibility, and so on. It's actually, though, this is this 80% fidelity, which is not that high, and there are several reasons for this. One of the reasons that can lead to, or which one can improve in the future, is that actually in these resonant gates, while you're driving your resonant transition, you're of course with the same frequency off resonantly driving another transition. So this would also then drive the target spin when the control spin is in the zero state. So that is something you don't want. So this red trajectory. And what you can then try, and this is sort of one thing that we propose, is that you can synchronize the two. So you can sort of adjust the ratio of the driving strength and the exchange coupling such that while this resonant transition makes a pi pulse, this off resonant transition makes an integer number of 2 pi rotations and ends up in the North Pole again in this case. This is what we call synchronization, and just glossing over this. So this is a condition here for the ratio of the exchange coupling and the driving strength, and so it's a certain square root of an integer that would then lead to an improvement of the gate fidelity. And actually, maybe just to wrap up here, there has been some recent progress that I mentioned before. For instance, there's one experiment from the Tarucha group that managed to do a fast C0 gate with this AC exchange method. That is this 99.5% fidelity, and they actually used exactly one of those synchronization techniques. So their ratio of exchange over the driving strength was square root of 15 throughout their paper, and so this is one of those synchronized settings. There's actually another way to circumvent this problem, which is using DC control. Then you don't have this problem, and this also leads to comparable fidelities. All right, so this is was very quick, and I think I should wrap up soon. I will just give you a very quick idea of what this last problem is. This last problem is that with exchange coupling, you can only couple nearest neighbor spins, and if you look at these circuits for our quantum algorithms, what you will find is that you actually also need to couple not nearest neighbor qubits. And one way of doing this is to combine the very long-lived spin qubits in semiconductors with superconducting resonators that can then mediate coupling between remote qubits. So maybe here I'll skip over this. This can be done with the flopping mode qubit. So the task is to couple your spins to electric fields. And this is again done with spin charge mixing with these magnetic field gradients. And so one important step that was achieved a few years ago by several groups was to reach the strong coupling regime in the coupling between single spins in these quantum dots to superconducting resonator fields. And the trick is really to find a way to mix electron spin with charge. With this mixing again, that's produced by the magnetic field gradient. that also produces decoherence. Unfortunately, the decoherence has a different scaling with the mixing angle, and if you choose the mixing angle small enough, you basically go near resonance, but not on resonance. You can find that your coherence improves more quickly. I mean, as you go away from the resonance, your coherence improves more quickly than your coupling decays, and this is how you can reach a strong coupling situation where the coupling between the spin and the photons G exceeds both the cavity loss rates and the qubit decoherence. And so this was then nicely demonstrated with these vacuum Rabi splitting experiments here. This is from the PETA group. There were other experiments in Delft and at ETH. And then from this, what we are dreaming of for the future, and I think people are already implementing at the moment, is to couple then two such qubits to the same resonator mode and use this to couple these two qubits over long distances. And so this is my final slide. So this is just the state of the art of these cavity mediated gates. So resonant coupling between two such qubits has been seen in these vacuum Rabi splittings. This is still spectroscopical detection, so it's not a gate operation yet. And actually what's interesting is that you can also use this coupling then to couple different kinds of qubits, for instance, a spin qubit to a superconducting qubit, and that could be interesting in the future as well. And I mean, you kind of use this superconducting microwave resonators as interfaces between different types of qubits. All right, so I think I've talked for long enough. I'd like to summarize. I've shown you the developments and maybe some of the ideas that led to the development of local C0 gates in these B-field gradients that now have quite impressive fidelities, but of course, there's still some work to be done to improve this. Also, what I've shown very briefly now is single spin photon strong coupling regime. And what we're striving at is now to make actually non-local quantum gates that could be between qubits that are, a millimeter apart or something like that, which is very far for these very small qubits. And yeah, we would also kind of have a prediction for the fidelity of those gates, and maybe we're thinking about how to further improve this. Another topic is how to read out spin qubits using microwave cavities, and how to use nuclear spins as memories, as I briefly showed you. Yeah, we've also written a review article on these cavity hybrid superconducting, semiconducting cavity QED systems, and in the near future, more or less, there will be, I guess, a review of modern physics on spin qubits as well. With this, I'd like to thank all the collaborators that have contributed to this. There's actually quite a long list. Particularly mention Monica Benito and Max Russ for what I've shown you today. Also Jonas Mielke on the nuclear spin coupling. And then we've had a very fruitful collaboration with the Princeton group led by Jason Pedder, and also with the additional theory support of Jake Taylor. So with this, I'd also like to thank you for listening. Thanks for hosting me here. And that's it. Thank you.
Great. Thank you very much, Guido, for this this very clear and comprehensive talk. And so we have time for questions. You can raise the hand or ask in the chat. I think there was one question by Jin Yang, which I didn't come to during the talk. So if you want to ask it now, I unmute you. You have to unmute yourself as well.
Hello. Yeah. Can you hear me?
Yes.
Yes.
Thank you for the very nice talk. I just have two questions. So in the earlier of your talk, you mentioned the nuclear spin environment. So I'm wondering, is it like, because it's like looks like a spin environment, how it is different from like for example, electromagnetic environment, which is like harmonic oscillators, when like, what would be the difference? Any difference you can see?
Yeah, I think there are some differences. I think so. The electromagnetic environment is typically okay. It's of course it has the electromagnetic environment has a variety of components, right? It could be that you simply have, let's say, you have Johnson noise or even quantum noise from dissipative parts of your circuit, from resistors, if you wish.
Right.
And that would then be basically described by a sea of bosonic, harmonic oscillators. There could also be two-level systems that have a different, and they have a different noise power spectrum. So these two-level systems just switch back and forth and produce this 1/f noise. And those you cannot typically describe by harmonic oscillators. And then the nuclear spins, I would also say that they have a different power spectrum. They have often a very dominant low frequency component, which is, and usually they're even non-Markovian, and typically I don't think they're very well described by a bath of harmonic oscillators.
Okay.
It actually depends on the physics of the noise source.
Yeah, I know. Like it has a, I don't know. It looks like this. Does it have, like, this charge noise has divergent spectrum density at the zero frequency? Is that right? So that's
it has this. Yeah, it has this 1/f characteristics which diverges. I guess there's usually a cutoff because experiments or quantum algorithms have a finite runtime. So there is a lower cutoff. Because they're not infinitely long, you cannot go. You actually never access zero frequency, but they can go down to very low frequencies, and then the noise becomes very strong at low frequencies. Yeah.
I wonder how, like in this case, how do series that dealing with these nuclear environments, because like you see there is this non-Markovian behavior and different spectral density from the bosonic environment.
Yeah, so that, I mean, I haven't shown any of that. There is a series of theory works from more than 10 years ago that has been dealing with this, and even the non-Markovian characters. So that this is actually a complicated problem. So it's one model that describes this is the so-called central spin Hamiltonian. It's related to this Robertson equation, and so it's in principle an integrable problem, but it's still a very complicated problem, and so that's one way people have been looking at this. And of course, what also is important is that the nuclear spins are typically in random states. They're not polarized because their energy splitting is so small.
Okay.
So this is an interesting problem. I think it's been treated with there's been quite a lot of very successful theory that also basically what it then predicts is a non-exponential decay of the electron spin, which can then not be described simply by this T2 time anymore, but which has more structure in its temporal dynamics. I would say that in the silicon systems with few nuclear spins, this is maybe not so important anymore. But of course, you still have the remaining silicon 29, and their number is not that big, but it still in some sense has to be dealt with.
I see. Thank you. Yeah.
Thanks.
Yeah, just like another question is that I'm just curious. Is it possible to do some error protection technique and dynamic decoupling or quantum error correction with spin qubits, like with current technology? Like for example, can you implement some error correction code, or is it like with the current technology? Is it possible to do that?
So actually okay. So this is something I showed you. So what you can do if you have this slow noise, so this we have very high component at low frequencies, basically means that it's quasi-static. So this is something that happens with the nuclear spins. So this has been So what you can then do is you can do dynamical decoupling. So the simplest version of that is spin echo. So basically, if the nuclear field is random but it's static, then you can make use of that. You can undo the effect of this random field by using spin echo techniques, at least for quantum memory. And then there is an extension of that. Is this are these pulses like this Carper-Cell, Mablum, Gill, I think, pulses, CPMG pulses that make this even more efficient. And then with this, you can extend the memory time in the presence of such a random field. And this has been basically pushed to the extreme by this work here in 2010, where in the presence, this is in gallium arsenide, and in the presence of all these nuclear spins, you have a billion random nuclear spins. Still, the effective coherence time, the phase was preserved over 200 microseconds. Whereas if you didn't do that, the coherence time would be 10 nanoseconds. So this is what one can do, and so there are all kinds of dynamical decoupling techniques that work for this kind of low frequency noise. And then usually you have that combined with higher frequency noise, and the higher frequency noise, or just kind of random stochastic noise, then typically what people try to or envision for the future perhaps to deal with this using quantum error correction. There you actually need an assumption usually that the error is uncorrelated, that it's doesn't have this low frequency component. So the combination of these two could work in the future. I mean, we are not in the area, we're not in the range yet where we have error corrected systems. So what I showed you, what Google did was not an error corrected system. In some sense, I think that's what they probably wanted to do first with their chip, but I think to kind of implement some error correcting code. But for this, I think even this 99% fidelity is not quite enough. And that's, I think, why they did this random circuit demonstration. And I guess in the future, people will try implementing error correction to deal with noise.
Thank you very much.
Thank you. Yeah, so there are two more questions. First by Wolfgang Schatke, then by Maxim Ilin. So please, Wolfgang. You have to unmute yourself.
Did you understand me?
Yes.
You use, I suppose you use a microwave wave. And what is a local gradient? What is the size? What should I?
Okay, so maybe you're referring to this AC-driven 2-qubit gate. Just go forward. So the gradient, what they achieve here with these micromagnets. So it's basically this J here. This gradient. So here, yeah, you cannot see the gradient here. It's indicated. So the difference in the resonance frequency for the ESR on the left and on the right is about 200 megahertz. So this is in frequency units the difference between the Zeeman energy on the left and on the right dot. Now you can translate that to Teslas. I think it's a few milliteslas, I think it's more like 100 millitesla or something like that. So those are the gradients you achieve with these micromagnets. These are cobalt micromagnets that are positioned onto the chip at the very last step after all this has been done. So this picture was taken before the micromagnet was put on. So, and I have to say, of course, I'm not doing these experiments. I'm just a theorist, but that's my understanding. So this is, and then the driving is done with microwaves, indeed. So the driving frequency is not given by the gradient. The driving frequency is given by the external field, and typically it's a few gigahertz.
Okay, thank you.
Sure.
Okay, Maxime, do you want to ask your question, or should I read it?
Hello, if you hear me, yeah.
Yes.
Okay. I just wonder if you could compare the semiconductor spin qubits with superconducting Andreev spin qubits. Do they have some advantages? How do they compare?
Okay, actually, maybe I don't know enough about the Andreev qubits. I guess so. So maybe if I can make it, I think the Andreev qubits don't require a resonator. Is that right?
Well, depends. If you want to drive, I mean, the basic difference would be that to let's say, instead of having this quantum dot in semiconductor, you have a sort of Josephson junction where you have trapped electrons in these localized states, and you can manipulate the spins. Anyway, so it's a different technology. It's not semiconducting. It's more superconducting technologies. So they
right. Okay, I mean the reason I kind of brought this up is that I would say one of the big differences, and I tried to make this point in the beginning, is that I think the most superconducting qubits, like the transmon is the type of qubit that most people are currently using, including IBM and Google. This is fairly large, and the reason is that they involve a critical component of this qubit is a superconducting resonator, and these resonators have to have a certain size. I think there are superconducting qubits that do not necessarily require a resonator. So the size is one thing that would limit you somewhat with scaling. What are the differences? I mean, I heard about these Andreev qubits, but I am not sure I know enough about them to sort of make a qualified statement. I think, of course, the main difference is that this qubit is a charge degree of freedom in some sense. You have a level which is occupied or not, whereas we are working with the spin qubit with the spin degree of freedom. But maybe the Andreev qubit is also one that is quite localized, so could be small. So this, but unfortunately, I don't think I can make a really valid comparison.
Okay, sir, thank you. And can you compare this, let's say, semiconducting qubits with what was proposed as these topologically protected qubits? Is there any progress in this field that can be compared?
Well, I would say, I would say that the topologically protected qubit in some sense promising, because if realized, it would have intrinsically, of course, a lot of robustness against noise because of its topological nature. I think the problem is it's not easy to realize, and I think they are still this field is even less advanced than this semiconductor spin qubits, because I think we're still waiting for a single qubit to be realized. So in that sense, I would say it has to be seen whether this works, and whether the noise properties are really, whether these topological qubits are really robust against noise, because I think it's not. I think that the problem is that with the topological qubits in their pure form with the full protection, I think it's known that you cannot do universal gates. So you have to sort of break the topological protection to some extent to make to produce a gate set which is universal, and then of course you lose some of the protection. But again, this is I'm not really an expert, but I think this is at early stages, and I think so it's even less advanced than in some sense in the development of the systems than the spin qubits. On the other hand, it's a very interesting physics, I think, that I find very, very fascinating.
Okay, thank you very much.
Thanks.
Okay, well, thank you. We are already a bit past 1, so I think we won't take more questions. Guido will be here until Thursday, and who would be interested in talking to him, please send me a line and we can arrange a meeting. And so I thank again Guido for his nice talk, and you for your attendance and your questions, and have a good afternoon. Bye.
Thanks.